Hi everybody. We're going to begin talking about Chapter 10, the last chapter that we're going over. It's going to be on parametric equations and polar coordinates. Okay, and the first section is 10.1, curves defined by parametric equations. So let me give you a little bit of background on this. So far, we have studied curves where y is a function of x. So as an example, a curve where y is a function of x, it looks something like, it does whatever, right? And so we are sort of limited here, right? Because the curve always needs to move to the right. It can never loop on itself or do anything interesting, right? Curve is always moving in one direction. Let's put it that way. So question though, what if we wish to study a general curve? What do I mean by a general curve? Well, let's suppose that this is our coordinate system, but our curve is doing whatever, right? We actually have a curve that can cross itself or do whatever. So obviously we cannot do that with our current notation, okay? So this is what we want to do. We want to study a general curve which we call C. How do we do this? We introduce something called parametric equations. So let me just say, since the curve never splits, right? Well, notice that the curve never split that I wrote down. It has one direction the entire time. X and Y must both be functions of a third variable t, which we call the parameter. Okay, so what this means is that x is a function of t and y is some other function of t. A lot of times what I will do is I will, instead of writing f of t, I'll write x of t and y of t, just because I don't like to introduce extra letters where they're not needed, right? So x and y themselves can be thought of as the functions, but the point is that they both are going to depend on t. Okay, how do we write this in vector notation? So this would be in parametric notation. In vector notation, it looks like this. Okay, this means the exact same thing. So these two guys mean the same thing, okay? This is called vector notation. Now, I know we've never spoken about vectors in this class, and technically this notation I'm sort of giving you a sneak peek of what's coming in Math 80, because in Math 80 you're going to keep doing parametric equations, except in Math 80, in multivariable calc, you're going to be seeing vector equations that look like this. There's an x, y, and a z part. Everything's going to be in 3D in that class. And so I'm just sort of trying to get you used to that by writing down the vector notation as well, okay? Now, we notice in this last picture that I drew that the curve does have a direction, okay? Do we all see that the curve is actually moving in this direction because of the little arrows that I drew? So a parametric curve always has a unique direction, okay? You could put little arrows throughout just to remind the person looking at it which direction it's going. But they always do have a direction. So how is that built into the equation? Well, it's simple, okay? We consider the direction of a parametric curve. So we have a direction as the direction in which the parameter t increases. And note, let me just say all parametric curves have a direction. So again, the way that you'll know which way they're moving is you could plug in two different t values, one small and one big, and then whichever way you've moved, that has to be the direction of the curve. Okay? So let me give you guys an example. So we're going to sketch and identify the curve. So first, x equals t squared minus 2t, and y equals t plus 1. This is an example of a parametric curve. So this is part A. How would we sketch and identify this? Well, what we could do is plug in, for example, different values of t, and then we could just see what points we get. I'll give you an example. Okay, if I plug in, I can create a little table for t, x, and y. And then if I plug in a value for t, let's say 0, then x and y are going to be determined, right? What would x be? Well, if I plug in 0 for the x equation, I get 0. And if I plug in 0 for the y equation, I get 1. So this actually led me to the point 0, 1. So I know that 0, 1 is on the curve. Now, rather than doing this for, 1,000 points and then getting an idea of the curve, maybe there's a way to actually write this as a function like the old-fashioned way. So notice we can, if you look carefully, we can actually write y, x, not y. We can write x as a function of y by solving for t. Let me show you what I mean. So if I take equation 2 and I solve for t, I get t is equal to y minus 1. And then if x is equal to t squared minus 2t, what I can do is I can replace the t in that equation with y minus 1. So I end up with x is equal to y minus 1 squared minus 2 times y minus 1. Okay, let's go ahead and actually simplify all of this, because right now we don't exactly know what curve this is going to be. So if I square this out, I get y squared minus 2y plus 1, and then I get minus 2y plus 2. So this ends up being x is equal to y squared minus 4y plus 3. Okay. What kind of curve is this? Well, x equals y squared. We know that this is going to be a parabola. And because the y squared part is positive, we know this is going to open right. Now, you might want to review parabola stuff from an earlier course. We are going to go over it in this class, but not until 10.5. So, hopefully you can review some parabola stuff here. But how do you actually graph this thing? Well, one way we could do it is by completing the square. Another way we could do it is by using a vertex formula. Let me show you the completing the square method, okay? This actually ends up, if you complete the square, you get this, okay? What this actually means is that the vertex of the parabola is equal to what? It would be negative 1, 2. Negative 1, 2. Because if you plug in 2 for y, x becomes negative 1. And this is your vertex. And it opens to the right. Okay? So we have a lot of information here. Let's go ahead and draw a picture of that. So negative 1, 2. There's negative 1, 2. And we know when it crosses, it's going to cross. Let me actually show you also that if I factor this out to y minus 3, y minus 1, this means we know it's going to cross at y equals, the y-intercepts are 1 and 3. So this means that it is going to cross here and here. Sorry, I should have really not... It goes in both directions, okay? Now, which direction is the curve moving? Sorry, this should be right at 1, and this should be right at 3, right? Which direction is the curve moving? That's a great question. We do need to make sure we put the correct direction in here. Well, I already know that t equals 0 gives me a point here, so now let's just plug in a bigger value for t. How about t equals 1? If you plug in t equals 1, y becomes 2, and x becomes 1 minus 2 is negative 1. So we're moving in this direction. This is my direction, from 0, 1 to negative 1, 2. Where are those 2 points? Well, if I put the dots here, this is 0, 1, and this is negative 1, 2. And so we know that we're moving in this direction. Okay? So there you go. We identified the curve. Notice that I only used the actual 2 points here to get direction. So this is how I got the direction. This is how I got the direction, right? I just plugged in t equals 0, and I plugged in t equals 1, and that gave me my 2 points. And I know I was moving from the first point to the second point because I plugged in a bigger t the second time. Okay, now this is part A. What about part B of this problem? Part B wants also for us to sketch and identify the curve, except this time there's going to be one little modification. The only modification here is that I'm restricting the domain. So this is just a piece of the curve in part A. So what piece would it be? Well, what we can do is, because we have a beginning and an end to this curve, I'm going to plug in t equals 0 and I'm going to plug in t equals 4 so that I can see where my curve begins and where it ends. If we plug in t equals 0, remember we already did that. We got the point 0, 1. So now that's the beginning of our curve. And if we plug in the point 4, we get, sorry, wrong one. Y is 5. X is 16 minus 8 is 8. So we know we're going from 0, 1, 2, 8, 5. So if we look at our curve, so here's 8, 5. Here's 0, 1. And remember, we knew that this guy has the vertex right there. So what does this curve do? It looks like this. So it's a piece of the parabola, and it goes from, I'm going to even label these clearly, this is 0, 1, and this is 8, 5. Okay? Does that make sense, everybody? So again, restricted domain. In the last problem, there was no restricted domain, so it just goes forever in both directions. So let's talk about some terminology here. Now that we're starting to learn a little bit more about how these curves work. So for a parametric curve, if you have a parametric curve that looks like this, with a function f of t and another function g of t, and t sits between a and b. As you guys saw in this last example, when you restrict the domain like this, this means that you have a beginning and you have an end, right? So r of a, which is going to be the point f of a, g of a, this is going to be the beginning, and we call this the initial point. And if you plug in r of b, this is going to be the point f of b, g of b. And this is called the terminal point. Okay, so we have the initial point and we have the terminal point. So as an example, your point, your curve may look something like this. So it might begin here and then it ends up over here. And so this would be the point f of a, g of a. And this would be the point f of b, g of b. So this would be the initial point, and this would be the terminal point. Of course, we use a solid dot if it reaches that, but if it doesn't quite reach it, but it goes infinitely close, we will put an open dot there. I will do an example like that later. Okay? Okay, let's keep practicing because, of course, the last example that we did, we could just write x as a function of y or y as a function of x, but you can't always do that, okay, because it won't always be a function. So let's go to another example. So this is going to be part A. What curve is represented by the following parametric equations. Okay, so the curve is going to be x is equal to cosine t, and y is equal to sine t, and t is going to go from 0 to 2 pi. Well, when you see cosine and sine, you may think to yourself, yeah, this is going to follow some sort of a oscillating thing, right? Circular thing, right? Maybe. So here's the key. Do we see a relationship between x and y that we could exploit? So I do, and hopefully you do too, especially in this course because we've been studying the Pythagorean identity, right, for sine and cosine. It's true, for example, that x squared plus y squared in this problem would just be cosine squared t plus sine squared t, which is equal to 1. So this means that x squared plus y squared is equal to 1. Okay? What does that mean? That means that actually this curve is the unit circle. Okay? So there's the unit circle. I'm going to sketch it. There's my unit circle. Okay? I should label that's 1, that's -1, that's -1, that's -1, right? So this is the unit circle, but it has a direction. Now we need to make sure that we talk about the direction here. So maybe what we could do is we could plug in a few points, right? So let's go ahead and do that, right? So we're going to have t, x, and y. Oh, there is also an important thing here that if t is 0, let's see where we begin the curve, because we should talk about where it begins and where it ends. We might not even get the full circle, right? But because it's 0 to 2 pi, we actually are going to get the full circle. If you plug in t equals 0, you end up with 1, 0. So we begin right here. And then which way are we moving? The problem is if I put in 2 pi, we actually see that we're still at 1, 0, which means at least we know it's 1 revolution around. But we need to know which way it's moving. And so the way I would do it is plug in a point that's close by, like pi over 2. And let's see where we are. If we plug in pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. So we're going from this point to this point. In other words, it's going counterclockwise. And it's 1 revolution. So let's be specific. Let me write down specifically what this is. This is the unit circle, counterclockwise, 1 revolution from 1, 0 to 1, 0. Okay, so this is my curve. Let me do a part B here. So part B. How about the following? So how about this one? And this one looks different, right? Because we've got a cosine of 2t and a sine of 2t. So certainly the parametric equations are not identical, right? However, we do notice that if we do x squared plus y squared, you get cosine squared 2t plus sine squared 2t, which is actually still 1, right? Because the identity holds no matter what values for theta you put in. So what does this mean? It means you still have the unit circle. That does not change. Something changes though. Let's see what changes. Well, I'm going to do my little chart. And I know that if I put in 0, I'm starting at the point 1, 0, right? So that doesn't change. And I know that if I put in 2 pi, I'm going to end at 1, 0. So what does that mean? Have I gone around once? Have I changed anything? Well, here's the thing to notice, right? Because those say 2t, it means that if I actually plug in pi, I still get 1, 0. So what happened? I actually have 2 revolutions, okay? This is revolution 1, and this is revolution 2. Okay? So it's like the problem from before, except I went around twice. So we're going counterclockwise, 2 revolutions from 1, 0 to 1, 0. We go around twice, so you could specify it like this if you wanted and draw another circle close by, just to sort of reiterate that we're going around 2 times. You don't need to do that though, as long as you write it down that this is 2 revolutions, unit circle. Interestingly enough though, if we had given the same curve, but we had gone from 0 to pi, we would get the exact same answer. And so the important thing to notice here is that parametrizations are not unique. Okay, so note, parametrizations of curves are not unique. What this means is that there are many ways of parametrizing any curve out there, infinitely many ways. Okay, so we're not going to talk about this too much this time, but as we move on in the chapter, we will bring this up again. Okay. Okay, let's try another one. Find parametric equations for the circle with radius r and center HK. So for those of you that may not remember this, I want you to recall from an earlier math class, probably pre-calculus or algebra, something like that, that the equation of the circle like this would be as follows. It would be x minus h squared plus y minus k squared is equal to r squared. So what is the trick here? The trick is to realize that this is going to have the exact same equations as before. We just need to make an adjustment. There are 2 adjustments to make, right? First of all, we want this thing to have radius r, not radius 1 like the unit circle. And also, we want to translate where these things are, right? That's the whole point of the HK. So here's the idea. The idea is that we want this guy right here to be r cos theta, and we want this guy right here to be r sine theta. Okay? Because if you were to square those guys and add them up, the relationship would work, wouldn't it? What is r cos theta? So r cos theta squared plus r sine theta squared is equal to r squared cos squared theta plus r squared sine squared theta, which is just r squared times cosine squared theta plus sine squared theta, which is just r squared. Okay, so what does this mean? How do we get it to look like that? So if we want to let x minus h be r cos theta, then this implies that x is equal to h plus r cos theta. And if we let y minus k equals r sine theta, then this means that y is equal to k plus r sine theta. So these are our two equations, and of course if we want to go around one time, we can just let theta go from 0 to 2 pi. So there we go. So in what we did here, note that over here, I use theta instead of t as our parameter, but it doesn't matter what you call the letter. Okay, I could have called it t the whole time. So if you had made this a t and you had called this a t and then you put a t here, it would be the exact same equation, right? What you call the letter doesn't matter. But I put theta there to remind us that this is actually, what this represents geometrically is the angle of rotation, right? Sorry, I wrote this wrong. I wrote is our parametric, but it should say is our parameter, okay? And we are moving counterclockwise, and this is 1 revolution, right? 1 revolution since I restricted it from 0 to 2 pi. Okay, let's keep going here. I want to do lots of different modifications of this so that you guys understand how to write the parametric form of a circle, okay? So how about this one? I want us to find parametric equations for the circle, or not for the circle, but for the ellipse, x squared over a squared plus y squared over b squared is equal to 1. Okay, we're going to learn in 10.5, remind you guys of how you sketch an ellipse, okay, in case you've forgotten how ellipses, hyperbolas, and all that stuff works. Now, we don't really need to understand how to sketch it for this problem. We just need to know how to write this in parametric form. So again, what we want is a relationship between the x and y variable. So again, think about ellipses. They are like stretched out circles, so the cosine sine trick will still work. However, it helps to figure out what is being squared here to give us 1. In the first one, it's x over a, and in the second one, it's y over b. So it makes sense to let x over a be, this time instead of theta, I'm going to use t. If x over a is equal to cos t, and if y over b is equal to sine t. What does this give us? Well, this means that x is equal to a cos t, and y is equal to b sine t. T goes from 0 to 2 pi. This is our parametrization of an ellipse. Okay. Again, this is counterclockwise, 1 revolution. So if A was bigger than B, this is what it would look like. There's A, and let's say B is up there. And that's negative B. It would look something like oops. Let me try that again. Something like that. Again, we're going to review. You don't need to sketch this out to do this problem successfully, but I just wanted to give you guys the sketch. We are going to review all this in 10.5. It's the last section of the course. Okay, let's try another one. How about this? This is number 5. So let's sketch the curve with the following parametric equations. Okay, this time it's going to be x equals sine t and y equals sine squared t. Now, I know that this might look tricky, right? We've got a sine squared there, we've got a sine there. So there's a lot to consider here, but what we start with is just to look for a relationship between x and y. So do we see a relationship? Well, since x is sine and y is sine squared, doesn't it make sense that y is equal to x squared? Right? Because, I mean, that should be obvious, right? Y is equal to sine squared t, which is the same as sine t squared, which is the same as x squared, right? Because you could look at the equations. This is just the square of that. So what does this mean? This means that what we are dealing with is a piece of the parabola. Now I'm writing a piece of the parabola because it may be the whole parabola, it may not. We need to examine this further. Okay, this one, something interesting is going to happen, okay? Because I want you to notice something. We know that sine of t, for example, always sits between -1 and 1. But since sine is x, this means that x goes between -1 and 1. So there's no way that we could get the whole parabola. Likewise, sine squared t, because you're squaring it, it can never be negative. It goes between 0 and 1, which means that y goes between 0 and 1. Okay, let's do a quick example here, or not example, but let me start drawing the picture here, okay? So I'm going to make this really big so we could see this. And so here's 1, here's 1, 1, here's -1, 1, here's 0. And so it's got to be this parabola, except because x can never go beyond 1 or -1, and y can never go beyond 1, this means that our curve, or our parametric curve, is really just going to be bouncing back and forth, back and forth, back and forth, back and forth, back and forth like that. So it goes this way, then it goes that way. The way I would visualize this is like this, and then it goes like this, right? And so we could see that it just keeps bouncing back and forth, back and forth. We can verify this by just plugging some stuff in, right? So if we had a t here, an x, and a y, for example, if I plug in t equals 0, remember we had sine of both, and one was sine squared, so that means you get 0, 0. In other words, it starts at the origin at t equals 0. Then at t equals pi over 2, sine of pi over 2 is 1, sine squared is 1. So if we were to write it out right here, at t equals 0, it's at that point. T equals pi over 2, it's there. Then when we plug in pi, Sine of pi is 0. Sine squared is 0. And so we're back to here. In other words, it just came back. And then at 3 pi over 2, so at 3 pi over 2, sine is -1, but sine squared is 1. So -1, 1, we reach the top of this. So let's write that down here. This is t equals 3 pi over 2. And then when we plug in 2 pi, we're back to 0, 0. Okay, so this is the pattern every 2 pi. Middle to right to left to middle. Right? So we got to be careful. It's not just about the relationship, but it's also about considering the domain. So let me talk about something else, okay? What if we have a function y equals f of x, and we wish to write it parametrically? Okay, this is easy. If you already have it in function form, that means you can translate it to parametric form right away, and you do that by just letting x be your parameter. And then y would just be f of t. It's that simple, okay? And if you have x is a function of y, then this means you can let y be your parameter, and then x is just the function. Okay? So it's not a difficult thing to do. This means, for example, if you had any function you could think of, like, let's make this example 6. So I want us to parametrize the curve y is equal to, I don't know, let's make this complicated, 3e to the x plus tan squared x. Well, because y is a function of x, you can just let x be t, and then y would just be 3e to the t plus tan squared t. And that's it. It's that simple. The point of this is saying that we can always take anything that any function that we've studied in the past, and we can write it in parametric form. That's easy. Okay, so this is really what we're doing is we're adding more language to what we already know, because the old stuff can easily translate into the new stuff. There is one more curve that I want to talk about because this curve pops up a lot in this chapter. So let me talk about an interesting curve called the cycloid. Okay, I want us to go over this because we are going to be seeing this curve quite a bit, and I want you guys to have a geometric idea of what this curve is. So what is a cycloid? So a cycloid is the curve traced out by a point P on the circumference of a circle as the circle rolls along a straight line. Okay, so let me give you an idea of this. Imagine if you had a floor, and imagine if you took, or even better, let's suppose you just thought of something against a wall, and you took a circle, let's say a quarter or something like that, and you have the quarter here, and you color in a dot. Let's say this dot down here, you call it P, and then you roll this quarter. You roll this quarter to the right, and I want you to look at the point P, and it's going to trace out a curve. So the curve that gets traced out as you roll this is going to look something like this. Right? Each time that it hits the floor, it means that it's gone around once, right? The point P. This red curve that I just drew, this is called the cycloid, or cycloid, however you want to say it, okay? But this is the direction of the curve. We're going to always assume that it moves to the right. Okay? So what we would like to do is we would like to come up with an equation for this thing, because this thing we can parametrize it. It's a little tricky, but it's not too difficult. We can do it just with trig and thinking about it a tiny bit. Okay? So I want us to consider that the curve itself, the circle itself, has a fixed radius. Of course, we've got to give the circle a radius. So let me actually start this discussion on the next line here. So I want us to suppose the circle has a fixed radius r. This is to remind you guys that even though r is a variable, it's fixed. Think of it as a number, okay? So fixed radius r, and rolls along the x-axis. So now we're giving a coordinate system to this. So it rolls along the x-axis, and we're going to pretend like the starting point, P, is at the origin, with P at the origin at a certain position. So let's find the parametric equations, okay? So let me go ahead and draw a picture of what would happen. So let's suppose that our circle, or our point, is right. So I need to draw let's suppose that our circle started at the origin and then it's rolled about this much. And let's say that the point P is right here. Okay. This is P. So what we want to do is figure out the coordinates of P. Now, remember, it started out as the origin, right? And so if what we essentially are trying to do is we're trying to figure out what the coordinates are of this point, right? We're trying to figure out what the x coordinate is and what the y coordinate is. So we want to figure out what each of these two dash marks represent. Let's say that the center of the circle is right here. So we know, for example, that from here to here is r, right? Because the circle has radius r. Okay. What else can we say? Well, we're trying to figure out the angle here. That would help. And so what we want to do is we want to choose the parameter now. So I want us to choose the parameter theta, which is going to be the angle of rotation of the circle. And so what we're assuming then is that this has rotated an angle of theta. So that means that if we started rolling the circle to the right, that this angle right here would be theta. Okay. So what does this mean? Let's start by thinking about how arc length works, right? So what we learned in trig is that anytime that you have a circle and a chunk of it, if this is theta and this is r, then the arc length is r times theta, right? Well, that's exactly what we have here. So what this tells us is that this piece of the circle has length r theta, but then that means that from here to here is r theta, because that's exactly how far it's rolled, right? If you want to talk about how far it's rolled, it's exactly how long the circle is. Now, I know I didn't draw this geometrically perfect, but I want you to use your imagination that those two are the same length, okay? So this is r theta, and that's important to know, okay? Now what? Now, to give myself a little more space to work with, let me erase this theta right here. Okay, I'm going to call it theta, but I want to create a right triangle here. Now notice that the coordinates of that right triangle have to be, so if sine of theta is equal to that dashed red line divided by the radius r, then that means that this dashed red line is equal to r sine theta. Okay, so what would this distance be right here? This distance right here would be the entire length minus the r sine theta, right? And so that gives us our x coordinate, right? This point right here then, that point must equal the whole thing minus r sine theta. So we found the x coordinate. Now what about the y coordinate? Okay, well, the entire thing is r, so let's say that r is up here, right? This is r, and then we know what this little piece is, right? How do we know? Because this is r cos theta, this little piece of the right triangle right there. And so this guy right here is r cos theta, just this little chunk right here. And so if I want to know what this guy is, then this guy right here is equal to r minus r cos theta. And so we end up with our equations of the cycloid, which is r theta minus r sine theta. That would be the x part, and the y part is r minus r cos theta. Okay? Now guys, you do not have to memorize these formulas, okay? Just understand that this is a curve that we're going to be dealing with a lot. The equations will always be given to you when you need them, but I just wanted you to see where they come from, okay? We're going to be looking at this curve again later in the next section, and also shows up in a lot of the sections in this section, okay? Thank you very much for watching, guys.